Thanks for taking the time to join this session. The topic of my session is safety in chaos, in particular, how to form realistic failure hypothesis. If you look back in the industry, in the information technology space in particular, the concept of chaos engineering is about 10 years old. It's not too long ago that we actually started talking about this discipline. And these, unlike other disciplines in engineering, whether it's safety, public safety, healthcare, hospital systems, incident responses, public for fire and police, different industries in industrial engineering who are focused on safety of people and equipment and human life, they had a much more longer runway on how to do this better. I think in the case of software engineering, we are still getting used to that idea. We like hearing stories about how different companies have succeeded in breaking things on purpose and what kind of value they got out of it. So, but instead I want to talk about what might actually happen in the real world. Because things don't go as expected. Your chaos engineering programs will face in fact some roadblocks. You will have to justify why you're doing it. You will have to justify why this matters at all. And so instead of talking about how it all worked out great, what kind of tools and technologies you can use, I want to spend the next 30-40 minutes on talking about what could go wrong, what are the kind of stumbling blocks you hit, and how do you deal with those stumbling blocks, and then talk about some lessons learned. If I were to focus on one topic today, one takeaway from this topic I want to give it up front is that it is all about learning from incidents. It's not about breaking things on purpose. It's more about learning from incidents. And that's what I'm going to talk a lot about in this talk. So my name is Subbu Allamaraju. I'm a Vice President of Technology at Expedia Group, where I joined 3.5 years ago, leading the cloud migration from data centers to the public cloud. So I spent a lot of time thinking about resilient architectures, how to get things right on the cloud, how to operate safely and securely and cheaply on the cloud. So as part of that, I spent a amount of time understanding how to improve resiliency. And I'm going to post, I have my Twitter handle there, and I'm going to post my slides in a week or so at my blog, subbu.org. In fact, there also you find some prior material on this subject in previous talks I gave, and as well as other material I published on that. Feel free to check it out. It's very relevant to the talk that I'm giving today. So let me start with the very definition of chaos engineering, because I want to put it out in the context so that we know what we're talking about. Chaos engineering is the discipline of experimenting on a system in order to build confidence in its ability to withstand turbulent conditions in production. I want to say this explicitly because there is still material out there that describes chaos engineering as something that is breaking things on purpose, breaking things randomly, like turning servers off, cutting network down, things like that. Instead, think of chaos engineering as a discipline of making calculated hypotheses of what might happen if you do a certain activity that is disruptive, like turning off a server, cutting a network, or introducing latency. What happens? So it's about making hypothesis and testing it. It's like A/B testing, no different. You make a hypothesis, on a control group you test the hypothesis and decide whether the hypothesis is right or not right. So I use a simple mental visual model to explain this even in simpler terms. Imagine a system in a stable condition. This is your production systems or whatever it is. It's operating in a stable condition. You introduce a turbulence to it. And you make an assumption of the fault is not, your fault line is where this vertical arrow is. That means if you tip the system up until the point, the system will come back to your stable condition. That's the hypothesis you're making. And if that happens, that is the case, the system will come back to the stable state, all is good. But if your assumption of your fault boundary is not right, let's imagine the fault boundary is somewhat before the turbulence, then you broke the system. So basically with chaos engineering, you're testing that hypothesis, you're making a bet and testing it in real life. So as you go through the rest of the talk, I want you to think of 4 questions. What is the system? Is it just your software, your configuration, your databases, your servers, network, storage, and so on and so forth? Or does it all include the people, processes, and tools? Keep that in your back of mind. Because when we say system, it is not just the software that is running on servers. It includes the people that are operating the system, the processes, and the tools. The second question, how do you form a hypothesis? Do you copy the work of other teams, other companies that have done? Would they work for you or not? How do you ensure safety so that you're not pushing the system towards beyond its fault domains? And then, why should anyone listen to you? That this work is important, this work is valuable, so it is important to allocate time and resources to get this work done. How do you make a case for this kind of work? Keep that in mind, because why break something if it is working? That's how we deal with software, right? All the time, we don't introduce new features if it is working. Same thing, why do you bother if the system is working? Keep those in mind. So let me take a step back and talk about a typical foray. This, in fact, is also my foray into this discipline of why you think of chaos engineering at all in the first place. It, in my case, started with cloud adoption, which is probably the case for a lot of you here, that you start adopting cloud, you are breaking down your monoliths, you start adopting microservices, you picked up the latest and greatest of cloud native technologies, and things are going well, you're picking up agility, you're releasing more frequently production, and then you get into a reasonable enough complexity and size and scale, and you're actually serving real customers. And that's when you start to think about, how do I build resiliency? Because you start to notice, with the changes you're introducing, sometimes there are outages, sometimes things are taking time, and you end up carrying pages of the weekends, and you sort of get worried about all these alerts. You don't know if you should get all the alerts or turn them off. Sometimes you have cloud failures, like the AZ failure 10 days ago in US East 1. And so these things happen, and you start to worry about, how do I actually get a handle of all this stuff so I can build more resilient software and then not worry about PagerDuty anymore. And that's when you realize, oh, there is this thing called chaos engineering. It's a light bulb that goes on your mind. That's what happened to me about 2 years ago. Oh, I could actually start investing in this field. So you read about it, you look at all the tools out there, you look at all the success stories, you get excited about it. It's actually sort of interesting to do it. You get a bit of rush doing that because you are actually introducing failures in real systems, and you can actually brag about it. But then the reality hits you. You go and talk to your teams. Hey, we are actually releasing this thing in production. Are you guys okay? So no, don't hit us, because you'll find some people saying, oh, let's do it, excited about it. But there are a lot of people that say, don't touch our systems because we have this mission critical stuff going on, or we have this major release that we are doing in the next 6 months, so don't bother us with this crap right now because we got to get that done. This happens a lot. This happened to me, and I'm sure this happened to you a lot. And so you end up disabling all those applications from your monkey exercises, and then you realize this one. Because you start killing randomly servers, you realize that it's actually not uncovering really major stuff, it's uncovering maybe trivial stuff, because you exclude all the things that will break. So you are limited with the benign things that you want to break, and they look fine. Probably they're in some CloudFormation auto-scaling groups, and so they come back up, you're not worried about it. And in fact, this is what happened in our case, because over a period of time, I was noticing what's going on is that we found cases where there was some AMIs that were deleted by mistakes by someone. The auto-scaling group, it failed when a server was taken down. Those are the kind of bugs we found. Nothing spectacular, nothing magical. It's sort of bugs that you have in your automation. And then, of course, you can't and won't test more serious failures. Because if you turn off database servers, you know that stuff is going to fall apart. You're not going to try region failovers because you're not sure if there are dependencies between your data centers. And you're not going to black hole systems because you know there are critical systems that serve a lot of other applications. So you're not actually testing and more serious failures. You're sort of stuck in this limbo, that wanting to do more but not sure how to make progress. That's when you begin to doubt your theory, doubt your idea of using this technology, this discipline, to actually improve resiliency. This is what happened to me. And then you get into the valley of misery. You don't know what to do. How do you get out of it? This is where my hypothesis is that, my observation is that a number of chaos engineering programs die there. Because you hit the reality, the excitement is over, you got stuck in the valley of despair. So how do you get out of it? Let's wipe the slate clean and imagine a null hypothesis. It's a very standard technique in mathematics. Imagine that chaos engineering has nothing to do with systems' capability to withstand turbulent conditions in production. And let's find proof, evidence, that actually disproves this hypothesis. How do we do that? We do that by changing the question from how do we make the system withstand turbulent conditions to how is the system actually behaving today in production? A shift away from how do I fix the problem to let's understand the problem. Very simple technique, very simple, basic. But then how do you understand what is going on in the production today? You can look at the as designed state of the system. The as designed is typically your documentation, your diagrams of the architecture, your code tells you the design state, your metrics, your logs and alerts, they all tell you as designed state. None of them are complete. They're all incomplete pieces of information that you can gather about something that is running in production. Imagine 10,000 applications in an enterprise, and you have no idea what those 10,000 are doing. You have some ideas of, vague ideas of which part is doing what, and you probably are familiar with some of them, but not all of them. So you have an incomplete understanding of what's running in production. So basically, your as designed state is biased towards what we think is running in the production. In fact, the metrics and alerts and logs we do are reflecting the same bias that we have about how it is supposed to work, not how it is working, because that's a starting point. So it's no good to look at the as designed state because it doesn't tell you much about what is actually happening in production. Instead, you look at the as it is state. How is the system actually working in production today? How do you do that? You look at incidents. Because incidents are the real world. They tell you what is going on in production, and they tell you how your architecture is working or not working. They tell you how your tools and processes are working or not working. They tell you how your people are actually able to deal with the systems. So it tells you about everything that's real, unlike the as designed state. So that's when I realized it's far more important to learn from incidents than to talk about or preach about what we should do to fix, improve resiliency in production. So that's what I ended up doing. I spent a number of weeks over a period of time, starting last summer, and then repeated during the December break, again during the July 4th break this year. I took a look at over 1,500 incidents that happened at Expedia Group. These are production incidents. I happen to have data of how long it took to recover, what happened in some cases, and how much revenue loss or how much impact, the customer impact was caused by those incidents. So I had this data, and the complexity of all that is that there are thousands of applications running in multiple cloud regions, multiple data centers, different architectures. None of it is consistent running in one way. There are multiple systems built over a period of time. So I tried to understand how those systems are, what those systems are telling, so I can actually help improve availability and reduce the customer impact. So that's what I did over a period of time, and this is what I found from that study of incidents. surprise, about half the impact was due to changes that we are making in production systems. Either a change is in progress or was recently made. This is not a surprise because you must have experienced the same thing in your own enterprises as well. And if you look at the publicly made incident reports by Facebook, Google, and other companies over years, you will find the same pattern everywhere. A config change or a code change made somewhere, some impact led to a customer incident, and you take time to recover from that. In the case of the sample I took, about half the impact was caused because of that. Sure, chaos engineering cannot help this situation. I have a different problem at hand. That's the realization I had. The second observation, again, this is based on incident logs. As a part of my study, I also looked at the Slack logs sometimes. That was very manual exercise, but I ended up doing that just to understand how people are behaving, dealing with the incident. What I realized is that because of the explosion of the number of components running in any enterprise today, right, it's fairly, even a young company, like 10 years old company, you will have thousands of systems running already in production. And we are over 20 years old company. So what the reality looks like that you have some tech debt that you can't get rid of. We all have that. You have some retired apps that you don't know if you shut off or not. You have some monoliths. We haven't fully gotten rid of them. We are transitioning, but we haven't fully gotten rid of them. And then you have thousands of microservices that you are changing all the time. So as a developer, as an engineer, or even if you're carrying a pager, you probably know what is so well about your application and your neighborhood around you, but not a lot about second order, third order systems that depend on you, or the ones that you depend on. So this actually makes incidents hard to deal with, because you don't expect an outage of your chain because of change or something 5 layers elsewhere. So this makes it difficult to troubleshoot incidents. Again, a natural consequence of complexity. The third observation that I had was that we don't understand where a failure stops. For example, if there is an application in one data center that failed, would it impact another application in another data center? We really don't know, because oftentimes we don't maintain clear fault lines in our applications. So what happens when you have a failure in one part of the system? You may have a cascading failure elsewhere that you least expect of. And that leads to long recovery times. So those are 3 observations I made out of this incident analysis. And in fact, if you go to my blog at subbu.org, you will find a much more detailed analysis, report of the findings. Feel free to check it out. And so what do these 3 observations tell us? First of all, improve release safety through progressive delivery. Again, we know this, but 2 years ago, before the analysis about incidents, when I asked teams, hey, how about doing progressively instead of pushing your code at the same time to multiple cloud regions? How about we stagger the releases over a period of time? And people looked at it as I'm crazy, because won't that slow us down? Yes, it would slow you down, but it makes it safe to release in the production. Now that I have data to showing that over 50% of impact is because of changes, I get a listening. People listen to what I'm saying because I have data to show that this stuff is important. The second point is that you have to have stronger failure domains, failure boundaries in the design itself. You got to make sure that there is redundancy and isolation between your components of your system. You can't have dependencies crisscrossing with multiple data centers and locations. Then you have a leaky fault domains and things cascade quickly. So you have to invest in the as designed state. The third is you have to implement safety. Again, we know this, but we don't necessarily come back to these ideas unless you see the data about incidents. How do you get safety in production? Of course, nothing phenomenal. You shed traffic when there is an incident, so you can actually preserve important traffic. You build independent fault domains. We used to call this DR in the past, which is nothing but having a separate copy of the application so you can actually fail over to that when there is something wrong. So you want at least 2 or more of those fault domains for your critical applications. You want to be able to shift traffic away when there is a failure in one case, because if you want to recover from an incident, a cascading incident in minutes, you better have a second copy that is working healthy. So you can shift traffic, because fixing a firefighting an incident is hard, it takes time. And of course, fourth, circuit breakers and fallback. Nothing new here. These are the technologies that we all learned over 20 years in the operating internet scale systems. But the incidents really tell you that you got to be good at these basics. And after doing all these three, is then you think of how do you break systems, because you have already built safety into your systems. Then you can make hypotheses about what can happen. This is in fact what happened to me at work. Today, we have many of our teams practicing multi-region failovers, because we had incidents where we want to recover in minutes, and then having these kind of investments into safety helped us precisely do that. I'll give an example. I was on Slack 2 weekends ago when the AWS AZ outage happened in US East 1, and one of my teammates was saying, I don't care because we already tested Route 53 between US East 1 and US West 2. No sweat, because the team has already invested in that process, tested it, and it is working. So that's a consequence of investing in safety before you try breaking stuff. But then, how do you make the case for these kind of failures? This is the hardest part. And I'll give an example. Last year, about a year 15 months ago, we had a long debate that happened over many weeks. The point of contention was, should we, as part of cloud migration, should we build a second region for some of the critical components and invest in failure testing before we call it done? And then we had both sides arguing. One side saying, yeah, we should do it because it's the right thing to do for customers and yada, yada, yada. And the other side saying, no, if you do that, it's going to cost this much more because you have a second copy running in production in a second region. It's going to take this much time because we have to implement this automation, failover, replication, all that stuff. And then one of my colleagues said, he actually did some math on a piece of paper. How much money do we make or revenue we get over a period of time? And then how much this line of business gets, okay, this percentage, we have some dollar number. And then how much does it translate to on average per minute? Okay, we have this number. And ask ourselves, how many minutes of downtime can we survive? Can we accept? Can we tolerate? Once looking at these numbers, folks said, oh, yeah, 15 minutes probably is the max we should do. Going beyond that doesn't look good. Okay, how do you do 15 minutes recovery from an incident? Okay, you got to have a second copy somewhere else. You need to have that second region running. Then you can do it better. So focusing on value instead of the anxiety of wanting to do this helped us shift the focus to, okay, how do we actually create that value for the customer and then use that argument to actually invest in this? Because for people making priority decisions on what to invest the team capacity for, it is important to have this data. Now once you have this kind of data, your product people or your leadership can make a decision, okay, should I invest in that feature that gets you X amount of money or does this for the customer versus this thing that actually saves reduce the impact to the customers? Then you can make an apples to apples comparison. Otherwise, you end up arguing for this kind of hygiene investments and you won't get prioritized quickly. So how did we get out of the valley of misery? One is learn from incidents. So instead of focusing on the as designed state, focus on as it is state and see what those incidents are telling you. Followed by making value-based decisions, because just because it is good to do doesn't mean that you should do it everywhere. You have to focus on where it makes most sense to do that kind of work. So you pick up your most critical systems, that's where you try it out. But that's where you also have to invest well upfront for safety so you can actually demonstrate that kind of recovery in minutes like the example I cited. The most important question is that how do you actually learn from incidents? There is no textbook that tells you how to learn from incidents. In fact, this field is so nascent. The common pattern that we all have is that incidents are bad. Incidents are not supposed to happen. And we treat an incident as though they happened because somebody or something or someone did not do as it's supposed to, as he or she or it is not supposed to do. Somebody had a bug that caused it. Somebody pushed a change that caused it. Something broke down in the network, the vendor caused it. That's how we think of incident, as though they're not supposed to happen. So there's no clear way to figure out how do you recover from learn from incidents. What do we do when we have an incident? We look at the impact and say, okay, we write a postmortem. That's a chore. We take it as a chore because we want to get it done quickly so we can turn our attention back to our sprint work and keep moving on. So we think of incidents as though they are not supposed to happen, so we don't spend enough time after incidents to actually process and learn from what is happening in our production environments. But how do you do this? I really don't know how to do that. I did one way, and I'm sure other companies are trying different ways to learn from incidents. But I can tell you something. How does it feel when you learn from incidents? When you have learned from incidents? And we can describe this way. You have better mental models of how the system works when it does and how it does not when it does not. That is, you are able to look at the system as a whole and be able to explain whether it is your architecture, whether it's your legacy components or lack of investments in certain areas, or tools, processes, and culture. You can actually make sense of these things when you learn from incidents. And you're not chasing symptoms, but are beginning to understand the system as a whole. That's how I felt it when I looked at incidents, because it told me that we got to invest in change safety, release safety as a number one thing. And that this data helped a lot of teams recognize that they need to be diligent about release safety, having pipelines that actually can roll back quickly, and those kind of improvements. So you're not chasing incidents, you are actually understanding the system as a whole. The third, you understand the role of people, process, and tools that play. The tone that a leader might use, the tone a team lead might use, a manager might use after an incident has an impact on whether we are learning from incidents or we are thinking of incidents as though they're not supposed to happen and they're bad for us and somebody made a mistake. So you could create a punitive culture or a learning culture, and a learning culture will actually let you learn from incidents, and then you can make systemic improvements. So you start to understand where you need to tweak your approaches so you can actually get the most out of incidents. And then you're able to articulate the value of hygiene investments. I'll give another example of this value hypothesis. Let's say you have a monolith that you're able to release maybe twice a month, which is not uncommon for large enterprises with big monoliths, where the code sits in a train, and then at the end of 15 days or 2 weeks, release engineering team takes that and then tests it, and then pushes to production over, let's say, or a weekend or midnight. That still happens in a lot of enterprises. And now you want to put a change in that. You want to introduce a feature into that, and that piece of functionality, and then it takes 6 months to introduce a feature. In 6 months, how many releases do you make? 6 into 2, 12 releases. That means you have the opportunity to learn at most 12 times from changes you're making. That's as fast as you can go. Because we know that getting feedback from production systems is important, so you want to release in small batches, and that's why we do microservices. But now you have a choice to make. Should I break out my code out of that monolith and do it quickly, or stay in the monolith, get the release done? Oftentimes, we actually do the later. We stay in the monolith, keep on pushing code to it because we got to get it done. We don't have time to refactor. But if you imagine if you refactor, it takes 3 months to refactor, and then you are making 5 releases a week. You're able to make a lot more releases in the aggregate. That means you're able to create value quicker and quicker because you reduce the time to value from 2 weeks to 1 day. So making these kind of arguments is important for engineers, because otherwise nobody will understand. Nobody will prioritize this kind of work. And we are the closest to the systems that we're running in the production. So what is the lesson from all this talk? Number one, learn from incidents, don't treat incidents as though they're not supposed to happen. In fact, increase the time after an incident to learn from what is going on and inculcate a learning culture. And that is the number one thing that I said. If your chaos engineering program must succeed, the most important thing to do is listen to what incidents are telling us. Number two, there's no number two. That's the only lesson. Thank you for that laughter. That made my day. Thank you very much. And I think we have some time for questions. So there's no microphone, but I'll be repeat the questions and then go ahead, please.
Yeah, so you mentioned early on in the talk that a lot of the sort of chaos engineering testing you were doing only really found trivial problems like some misconfiguration or some pretty like basic problems. And later you said when you talked about learning from incidents that somehow allowed you. Do you have any specific like example of how you can do that better? How like maybe you
Is the
but were you like, are you now like testing things that failed during an incident or?
Yeah, so the question is, are you actually testing things after an incident and then are you doing the incident so that you are actually getting better at over time? I think absolutely. What I have seen over this time is that the teams that are paying attention to incidents, in fact, this analysis I published when I published internally late last year and again multiple times in increments, internally, it lit up a lot of teams. Teams realize, holy crap, this is what is happening. Let us go back and look at our own systems. So teams have done their own analysis within their own their applications and then realized where the opportunities are. Some teams invested in having the redundancy and then were testing failovers between region failovers and things like that. The other teams who said, okay, we got to fix our pipelines so that we can actually roll back quickly. So so each team took the time to look at their own systems and figure out what they need to invest in to get this going. So it's an organic movement instead of a systemic top-down mandate of, hey, we got to do this right now. So we never had that kind of mandate. It's more organic based on the data. I think that actually worked out better because people felt more passionate about what they're doing and the value they're creating to this work. Yes, please.
How do you break up a culture of fear of blame and finger pointing and it's not my problem, it must be somewhere else?
This is a tough one. I think over time I realized that I think the systems are complex. The most production environments are complex because of the number of changes we make, the number of components we have. Very few enterprises have the green field. We always operate in a gray field where you have some young systems, some old systems, and none of us are long enough to know all of the systems. It's humanly impossible. Once you realize that our systems are reasonably complex, we don't understand enough of what's happening in production. We know a little bit here and there. I know the code I wrote, but not the code my teammates are writing. I have a vague understanding of what they're doing, but I don't fully understand all the assumptions they're making. So once you realize that we are making different assumptions about how different systems are supposed to work, and we are designing and implementing based on those assumptions, then your attitude starts to change. And as our assumptions can be wrong, and we of course want to improve our assumptions, but we make assumptions. And this is in fact what is happening with the proliferation of microservices and other systems, because we are making more and more assumptions about the layers we depend on, the layers that rely on us. There are a ton of assumptions, and so those could go wrong. And then I think once you take that approach, it becomes easy to say that it's humanly impossible to understand and make sure everything is done right. What we can improve is the culture and processes and tools, so we can actually catch things sooner and have the ability to react to these situations quickly. I'll give an example. I was talking to a friend of mine, a close friend of mine, about a year ago, who joined a large cloud company in the Seattle area. And the part of this, their team runs bunch of new systems, and they scaled rapidly, and most of the team members are either fresh out of college or are really new to the team. They were all carrying pages, and this friend used to carry a laptop when he used to come to our house on evenings. Like, why did you buy the laptop? Oh, I'm on pager duty, on call this weekend. So there was stress, obviously. And I met him about the other weekend. We were hiking, and I asked him, how are things going? He said, things are much better. He was on pager duty, but things are much better. I said, what changed? Did you refactor, reinvent something? You did something better drastically? He said, no, it just, we got used to it. We actually know much more about our systems now, so we can react quickly. So in a sense, what he's telling is that we actually learn a lot from the postmortems we are writing. We have a better sense of what is going on, so we can actually quickly tell. And time is a creates an opportunity to learn from systems. So there's a drastic change without actually investing anything in production. So that's the consequence of learning. I believe in that process. I think if we stop thinking of incidents as they are not supposed to happen, instead they are a consequence of reality in the world, then we have a much better control, I think. Any other questions at the back? Yes, please.
After a post-mortem where you write out the changes you have to make to address the root causes, in your experience, how have you ensured that your team or you have actually made those changes and they haven't just been stuck in the backlog and never addressed?
It's a very important question. The question is that how do you ensure that after an incident you have a post-mortem and you have identified a number of action items, how do you ensure that actually teams are actually doing all that? No, I don't ensure that. And here's why. If I'm giving an exaggerated example. Let's say you have an incident once a week. Not uncommon. In large systems it happens. And then you have a team of 20, 30 people. And if you have an incident every week and you have 5-6 items from that incident post-mortem to work on, over time your backlog fills up. And you don't get the time you will not have the time to act on all those backlog items. And it feels bad because you're not taking care of hygiene. The things you say you want to do, you're not actually getting the time to do them because you have other feature work that's piling on you. And so I think instead of worrying about fixing all items, I would actually look for patterns and look at the value. And once you shift your focus towards, are there patterns that I can actually look at of all the incidents? Maybe every month or 2 months you sit down and look at all your incidents. Okay, are there patterns between those incidents? Are there common things that I actually invest in to improve what is going on? And then while you do that, you can also see which of those things actually reduce the customer impact. So you look at systemically like what you could do instead of going after each incident, because you will not have enough time to go after each incident to fix everything that you need to fix. But if you look at patterns, my hypothesis is that you will have the opportunity to study what improvements you need to make, and then how much value those improvements will provide. And then you can actually argue for getting those investments made. I think so that's the way I look at it, RCA outcomes. I mean, I'm sure there are different perspectives on this, but this is how I'm learning to see this. Yes, please. Absolutely, because it becomes real. Because then you know what assumptions that need to be tested. Because you already built enough safety into your system, but you still want to make sure they are being tested. So let's say we have traffic peak times through a year. In any e-commerce business, you have traffic peaks. And we do want to make sure that our systems actually meet the traffic. So we go through tests of, okay, are the auto scaling groups working as expected? Are we able to shift traffic if we have to? So you go through those exercises to prepare your systems for the real world. So there is still value, but it's not just isolated. It's all connected in the same scheme of things of how do I improve stability, how do I get most out of incidents and things like that. Any other questions? I think we have 1 more minute. If not, thank you very much. I'll give that. Okay, it's time. Thank you.